Welcome everybody to this edition of the ICTS string seminars. I hope everybody is doing well in these tough times. Today we are delighted to have Juan Maldacena with us, and he's going to talk to us about his recent work on magnetic black holes. So over to you, Juan.
Okay. I guess, can you see my screen or not?
Not yet.
No? Okay.
Not yet.
No, okay, let me just make sure.
Okay, now
okay.
Yeah, that's fine.
Well, hello everybody, and I hope everyone is doing well. This talk will be based on this first paper, and it really is an expansion of some remarks that in a previous paper that we wrote on with Milekin and Popov, which talk more about wormholes, and I briefly mentioned that. I will briefly mention that application at the end. Okay, so the basic idea is that we will discuss some aspects of magnetically charged black holes in the standard model of particle physics. So the motivation is that magnetically charged black holes are long-lived configurations which are compatible with the laws of physics as we know them, of course, provided the U1 is compact. And maybe they were produced in the early universe, and we should, in principle, understand their properties if we want to discover them or rule them out. And they basically, the main message is that they have some interesting properties because they can have very large magnetic fields. Now, these interesting properties, as I said, they are based on having very large magnetic fields, and they are, in some sense, a natural way of getting very large magnetic fields. Natural in the sense that they are compatible with the natural laws we know, but also theoretically natural because it's a very simple configuration that gives rise to very large magnetic fields. And there are two interesting properties that I want to point out. So one is that the electroweak symmetry can be restored around the black hole. And the second is that the standard model fermions give rise to a large number of effective fields moving in and out of the black hole. And this greatly enhances the effects of Hawking radiation and leads to sort of a faster evolution for the black hole as compared to the ordinary Schwarzschild black hole. And also due to the fact that black holes do not preserve global symmetries, they can also catalyze variant decay and so on, violate some of the global symmetries of the standard model. Now, the starting point is just the standard charged black hole solution. Here, I've written just the extremal solution, but one could also consider near extremal solutions. Of course, one might think about very far from extremal, but we are mostly going to consider extremal or near extremal solutions, since we were interested in sort of all the black holes. Now, so we have the usual metric. The metric is just characterized by an overall length scale, the extremal radius, and that radius, by solving Einstein's equations, is given by this formula, which is basically proportional to the Planck length times an integer, and this integer is the amount of magnetic flux through the sphere. So the magnetic field is seen in this formula here, and it's of course it's given by some. Well, here is the integer that fixes the flux, and it's related to the ordinary magnetic field by usually the factor of E. We're going to define F to be E times B, so B is just what's normally called magnetic field. So in our notations, then the magnetic field goes like 1 over r squared, and the coefficient on the top is the charge Q. So in this type of black holes, there will be two scales that are relevant for the physics. So one scale is obvious, is this size scale that we are discussing. It sets the size of the black hole, the size of the throat, the typical size here of this throat mission. And these, and also the size of the sphere at the, well, so this geometry in the near horizon region is ADS2 times S2. This is not too important for what we're going to say, but it's also the size of the S2. Now, second scale is the square root of F. So this is an energy scale. F has units of 1/length squared. And this will be important because this will be the typical energies of Landau levels for charged particles propagating in the black hole background. Now, the important point here is that these typical energies will become small when Q becomes large. So when the black hole becomes very large, the magnetic field intensity, so the proper size of the magnetic field, will become relatively small. Now, so when you have a charged particle propagating in a magnetic field, of course, the problem is translation invariant boost invariant along the direction of the magnetic field. So the spectrum will be an effective mass, could be written in terms of an effective mass for the problem in 1+1 dimensions, where the one spatial dimension is along the magnetic field. And if we have a field with some 4-dimensional mass m, then this 2-dimensional mass is given in the lowest mass that we will have for each field is given by this formula, where we have the magnetic field that we have here. So here we're thinking of a constant magnetic field in flat space along the third direction. And then there is a factor that involves the spin of the particle. So here is the spin of the particle. And for spin 0, then we'll have a formula which tells us that we have the mass square plus some positive energy due to the energy of the lowest Landau level. For spin 1/2, there is a cancellation between the orbital energy that we already had for spin 0 and a coupling between the magnetic field and the magnetic moment of the charged particle. And that gives an exact cancellation, and you get 0. So now it might be a little surprising that we get this exact cancellation, but it's a consequence. You can view it as a consequence of the chiral anomaly. So if you have a massless field in 4 dimensions, there is a four-dimensional chiral anomaly. And when you put the magnetic field, that 4-dimensional chiral anomaly translates into a 2-dimensional chiral anomaly. So in order to have that chiral anomaly in 2 dimensions, you have to have massless particles in 2 dimensions. So this is how you can, this is one way to understand it without doing any calculation. Of course, it's not complicated to the calculation, and explicitly check that you have these massless modes. And then if you have, on the other hand, if you have a charge vector, so you have a spin 1 particle charge under this magnetic field, well, carrying electric charge, then the magnetic moment contribution can actually overwhelm the orbital contribution, and we get this minus sign for the lowest level. So that's why, let's say, magnetic fields can be screened in non-abelian theories. So here, in deriving this, we assume that the coupling to the vector is that which you have in the standard Yang-Mills Lagrangian. And this will be an issue for the W boson, which is a particle charge massive vector, and we'll see that this leads to an interesting effect. And then we have all the other Landau levels, and they are just spaced in units of 2f. Okay, so if we had just massless fermions, then and a very large magnetic field, then we have a bunch of fields at 2-dimensional fields at these masses of 2f, mass square equal to 2f, and so on. And we would have a massless mode that comes from this original particle here. Okay. Now, we said that in our problem, the magnetic field goes like Q over R squared. And the largest magnetic field is in the near horizon region. And we will have to put R equal to the extremal radius, Q over R squared, but the extremal radius is proportional to Q itself. So we get a magnetic field which goes like 1 over q, right? This is what we said before, that the magnetic field becomes smaller when q becomes larger. And it's very large for very small q because of this coefficient of 1 over L Planck squared. So it's a very large magnetic field. And now the electroweak vacuum will be unstable when the magnetic field becomes as large as the mass square of the W boson. Okay. Now you can look at the black hole formulas and ask when that happens. And that happens for a Q which is equal to this value, so 10 to the 32 or smaller. For Q's larger than this value, the magnetic field never becomes large enough. So, and this particular value of Q corresponds to a mass of order a few times the mass of the Earth. And that's a size roughly comparable to the size of a pool ball or a billiard ball. Okay, so that would be the actual size of the black hole when this magnetic instability first appears. Okay, so and in those cases, then the electroweak vacuum will be changed near the black hole. So if we had a black hole of this size, we would have that the electroweak vacuum in the near horizon region is changed. And so we have a somewhat macroscopic object, which where the electroweak vacuum is different from our own. And we'll discuss a bit what that is. Now, when this W bosons condense, so let's say the magnetic field is much larger than this value, so then the W bosons will condense, and what we expect that the next result after they condense completely is that we will screen completely the SU2 part of the magnetic field. So I remind you that so a standard model has the gauge group U1 times SU2, and an ordinary electromagnetic field is really a superposition of a magnetic field in the hypercharge direction. So this Y direction, this is the generator hypercharge, and then in the third component of the SU2 of the gauge group. And we start out an ordinary magnetic field. We start out with two equal values in both the hypercharge direction and the SU2 direction. And after the SU2 is screened, we will be left only with the hypercharged magnetic field and no gauge field in the SU2 part.
Sorry, Juan,
yes,
can I ask a question, or I shouldn't interrupt?
Yes, please, yeah.
Okay, I'm just wondering, since the W boson carries spin unlike the Higgs boson, if it condenses, will it do something to the the spherical symmetry of the horizon?
Oh, good. Yes. When I say that it condenses, I merely say that it acquires an expectation value.
Yeah.
And the expectation value will not be translational invariant. It will break the rotational symmetry in general. We'll discuss that a bit more later.
Okay.
But after this process is done, after it's done completely, we regain the spherical symmetry. I'll discuss it later. So,
thank you.
Here I only wanted to make the point that once the SU2 is gone, the Higgs is now charged under the hypercharge, and so it will have this positive contribution to the energy due to the Landau level. And so normally around the minimum, around the H equal to 0 point, so the value where the Higgs is 0, the potential is negative, but we'll get a positive contribution from the magnetic field. And if the magnetic field is large enough, that will be a net positive contribution, and the Higgs will be driven to 0. Okay, so for very large magnetic fields, the electroweak symmetry will be restored. And this was, the whole process was studied in detail in some papers by, very nice series of papers by Ambjörn and Olesen. And then there were also some further more modern papers. These were papers in the 90s, and now there are some more modern papers that discuss this in the context of, let's say, flat space and a uniform magnetic field. If we start from very high magnetic fields where we only have the hypercharge component, so this is again saying the same thing that I said before, but with some formulas. So we start with the potential for the Higgs around the origin, around H equal to 0, which has a negative coefficient. And then we have the positive coefficient from the magnetic field. And so this whole coefficient becomes 0. when this condition is obeyed, and this condition is equal to the condition that the magnetic field is equal to the Higgs mass. Okay. Now, something that will be important for our discussion is that the Higgs mass is bigger than the W mass. Okay. So then the final picture is the following. So we're imagining now a black hole whose charge is less than the charge corresponding to a black hole of a billiard ball size. And so such a black hole will have a core here in this central region. So the black hole is, let's say, small, and then it will have a region further out where there will be something interesting happening with the gauge fields of the standard model. So near the center, we will have purely the hypercharged magnetic field and a zero Higgs web. So in this brown region, we have H equal to 0 and purely hypercharged. And this will happen up to a distance where when we are at the distance such that the magnetic field is equal to the Higgs value, to the mass of the Higgs squared, then at that point, we'll start condensing the Higgs, okay? So from that point outwards, there will be some condensate of the Higgs. If we only had the Higgs, we would just condense the Higgs, and this would be some formation of some kind of vortices, similar to the ones you have in type 2 superconductors, if the Higgs were just a single complex field. Now, that's not exactly what we have, and so what we have is that there will be a condensation of the Higgs and also of the SU2 components of the gauge field. They will start becoming non-zero in this yellow region. But by the time we are out to a distance where F is equal to the mass of the W squared, then at that point, the W bosons will become 0 again. So in this region outside, we have ordinary magnetic field, and we also have the ordinary vacuum. The ordinary vacuum with Higgs equal to the Higgs web. And so in this yellow region in between, there are two things that are happening. One is that the Higgs is increasing from 0 to the value to the web. And the other is that we have non-trivial values for all three components of the SU2 gauge fields. Now, it turns out that the solution cannot be spherically symmetric, and so there is a breaking of the spherical symmetry. This yellow region, if we took a little flat segment, so for very large radius, this sphere, well, is very large, and we could consider some segment of this sphere. And in this segment, we will have some kind of lattice, it seems to be a triangular lattice of objects, of regions where the gauge fields and the Higgs and so on are oscillating. They have some oscillatory values and so on. And the mean value of the Higgs, for example, will be increasing from 0 at this point to to the usual web at the outer boundary of this region. So we call this yellow region the electroweak corona, because it's sort of somewhat similar to the magnetic corona, that solar corona, sorry, that I have here in the background. This corona can be much larger than the size of the black hole, because the size of the black hole goes like Q times L Planck, while the radius of this corona goes like square root of Q times MW, or M Higgs. I mean, for the purpose of this argument, they're more or less the same. And so but L Planck and 1 over MW are very different length scales. So 1 over MW is a much bigger length scale, but the dependence on Q is slower. So there will be a whole region in Q where this radius of the corona is bigger than the radius of the black hole.
Sorry, I have to ask,
yes.
Juan, no, sorry, this is a joke. Did you choose the word corona just by coincidence, or never mind? Sorry.
Or you will see, you will see.
Okay.
Well, I thought it was very appropriate.
Okay. Right.
So so this is the same thing that I said before. So this is a little plot of the charge. So as a function of the charge of the black hole, the radius, and yeah, so this is the blue is the radius of the black hole, and the so here in orange I have the radius of the corona, and you can similarly define a QCD radius where the QCD vacuum is also distorted by the magnetic field when the magnetic field is larger than the than lambda QCD, and so you can also define that radius. So this point where the electroweak radius and the radius of the black hole coincide, that was the billiard-sized black hole that we discussed that has a mass of order the Earth mass. And then you can, well, you can here look and say, well, I don't know if I have a mass, I don't know if a few hundred, well, here you can see, I mean, you for masses within this range, you have, for example, the QCD radius comparable to the atomic radius and so on. Okay, so here I'm going to discuss some qualitative aspects of this electroweak corona. This is not really how it looks like, but just something a little bit qualitative. So if we had a magnetically, yeah.
I have a small question, Juan.
Yes.
If the size of the black hole is so small, then its temperature must be very high, right?
Ah, good. So yeah, so the relationship between the size and the temperature holds for the Schwarzschild black hole, right?
Yes, yes.
But this is a charged black hole, so the temperature is a separate parameter, and so when so when the black hole goes to extremality, its temperature goes to 0. So you can have a very small black hole with a very low temperature.
I see.
So for example, yeah, so you can have a black hole here of 100 kilograms, and its temperature could be very close to 0, and it would be a very tiny object. Okay, so you have very tiny. I mean, the black hole itself will be very tiny, so it's up here, but this electroweak corona radius can be much larger. So, for example, it could be, let's say, the radius of the proton.
Okay. All right. Thank you.
So, yeah. And here, for example, and in the top region, well, these are very heavy black holes, but you can have a macroscopic size region where the electroweak symmetry is restored, right? So a region of a few centimeters, few millimeters. So there is so the qualitative aspects of this electroweak corona. So the magnetic, imagine you had a magnetically charged black hole in the abelian Higgs model plus gravity. So here I'm imagining just a model with a single complex Higgs boson, Higgs field. So in this case, we expect a similar picture where we have the black hole at the center and a region where the Higgs, the brown region is where the Higgs value is 0. And then we will form, when we go out, in the faraway region, the magnetic field will be confined into this Nielsen-Olsen strings, so the strings of the abelian Higgs model. And so this is roughly somewhat similar to what we would get in the standard model if we remove the SU2 gauge fields. The standard model, that would be slightly different because there would be two complex Higgs fields, but it's somewhat similar. And the new feature that we have in the SU2 case, once we add the SU2 fields, is that these strings can end on monopoles. And so conceptually, we have roughly like the formation of these strings, and then they end on the monopole. It's not quite this picture. It's more similar to the other picture that I drew before, where there was a region, a more spread out region, and region where we don't have well-defined magnetic monopoles. It's all distributed. But anyway, so if you draw this picture, then that's, I guess, another reason for the name.
Sorry, one question.
Yeah.
Hello? Yeah.
Yes, please ask.
So far, did it have to be a black hole? If you had something which is
good question, very good question. Yeah, no, it did not have to be a black hole at all. So this is true for anything where. So let me go back to this picture. You would have this picture for any situation where you have a localized source for hypercharge, right? For the hypercharged magnetic field. So for example, if you had a bunch of GAT monopoles and you collect them into a very small region of space, then you will have, again, this picture. Mm-hmm. Now, the GAT monopoles will repel, yeah. So what makes the black hole special is that they are somehow a natural source. Natural in the sense that, well, they're at least metastable source. I will discuss the instabilities later, but well, not instabilities, but metastabilities and decay channels. But it's hard to get together all these monopoles. But if you had some way of having, or some maybe different laws of physics at very high energies that want to pull all these monopoles together, then you would have exactly the same feature.
Okay. And just one more question: doesn't this presence of this condensate, does it change the fact that we are at extremality, or it's the
Yes, I will discuss that. Yes, okay. It does. So, well, you mean the mass equal to charge condition?
Yeah.
Yes. Well, I mean, maybe I could just start saying that here. So this process of the formation of this corona lowers the energy of the black hole, right? So right. The extremal black hole solution that I discussed in the very beginning, that I wrote in the very beginning, is correct even in this region of parameters, right? So that's an allowed solution and has that mass. When this whole structure forms, we lower the energy, and then we have some smaller mass.
Okay.
Yeah.
Okay. Thanks.
Sure.
Sorry, Juan, I must have misunderstood something. You wrote an extremal black hole solution, then you lowered the mass. Sorry. Wouldn't that violate the extremality bound now, or there's a new extremality?
Yes, it violates the extremality bound. Yes.
Oh, okay. Fine. Thanks.
Yeah. Oh, this was coming here. So yeah, this is exactly this first sentence that I had here. So, and this lowering of the bound is what we expect from weak gravity ideas, right? There should be objects with m less than q, and this is, well, one possible object. And as we just discussed, it doesn't have to be a black hole. Now, there was one solution of this kind that was discussed in the past, which was the case when q is equal to 2. For that particular case, and only for that case, there is a possibility of having a spherically symmetric solution. And so that solution consists of a Dirac monopole for hypercharge, sort of at the origin, and some kind of SU2 monopole around it. In general, for q bigger than 2, it's not spherically symmetric. Okay. One final point is that this magnetic corona, is not present for the q equal to 1 GAT magnetic monopole, and that's because this magnetic monopole also needs some SU2 and SU3 magnetic fields. So there is when I said before that you can screen the SU2 component of the magnetic field, that wasn't exactly correct. We can screen basically all of it except a particular some C2, except some small value. And the more precise reason is that is the following. So we've been normalizing Q to be basically the usual units of magnetic charge for the electromagnetic field, but in hypercharge there are fermions that carry fractional values of this charge, and that would not be compatible with this quantization of the magnetic field. But it is compatible if we assume that the whole gauge group of the standard model is really U1 times SU2 times SU3 divided by C6, so that the objects that carry fractional hypercharge also carry either SU2 or SU3 charges. And well, this type of course, this could be the gauge group of the standard model. And in fact, if you get the standard model gauge group from a GAT theory, like SU5 and so on, you get this particular gauge group. And so in the particular case that we have, let's say, Q equal to 1 for hypercharge, then we also have some fluxes for SU2 and SU3, some discrete fluxes for SU2 and SU3. Yes?
Sorry, Juan, you mentioned it briefly, but just to ask you, when the magnetic field already gets to be of order lambda QCD, I suppose the QCD vacuum itself will undergo changes because some of the quark condensates of charged quarks, etc., might, I don't know.
Yes. So this has somewhat been discussed in the literature. I have not completely understood the literature, so but well, there are some papers saying, well, look, the raw meson also has spin 1, and so the argument we said for the W boson could be applied for the raw meson, and then you could have a condensate of raw mesons. So that's a simple argument.
I see.
But
okay,
yeah.
Thank you.
Yeah, so there are a few papers there are several papers in the literature studying QCD for large magnetic fields, especially in the region where you are close to this instability we just mentioned of magnetic fields, that you condense the raw meson, or exactly what happens in this region, and that has some interest for, let's say, heavy ion collisions and stuff like that. But I certainly have not looked at this in great detail.
Thank you.
Okay. Yeah, so there are more things that happen in these black holes than the ones I'm highlighting. So I highlighted here the electroweak one because it's something simple that can be understood in the classical theory. The questions about QCD are more complicated because they involve non-perturbative effects in the Yang-Mills-Lagrange. Okay, so now, so we discussed so far this formation of the corona, which is purely a classical phenomenon. But now we can also discuss more quantum phenomenon, which can be understood perturbatively, which is the behavior of fermions in this background. So the standard model fermions. So in the region where the electroweak symmetry is restored, they are all massless. Okay, so the fermions of the standard model are all massless, and they are all charged under the magnetic hypercharge, and so they all have some zero energy Landau level, which has the degeneracy, which is equal to this number. Okay, and this lead to massless modes, to effectively massless two-dimensional fields, which propagate along the radial direction and time, and they can be, well, they can be viewed as moving along the magnetic field lines, sort of one massless mode per flux quantum. In other words, when you think about the Landau levels, you can choose sort of different orbitals, and you can somehow localize you can roughly localize an orbital around a region which is of order one magnetic flux quantum. So you draw a little disk of a size of one flux quantum, and that's roughly the size of an orbital. Okay. Of course, you can choose these orbitals in many different ways. You can choose them with axial symmetry, and then they look like little strips going around the North Pole or of the sphere and so on. Okay. And also, I guess I could mention that this quantity here, which is the degeneracy, is also the angular momentum of the fields. Well, this 2L plus 1 of the modes that we are discussing. Now, so all of this transparency is about what the fermions are doing in the region where the Higgs is 0. When we reach this electroweak corona, some of these fermions get the mass, some more mass than others, and also some become neutral, like the neutrino, and then you lose this very large degeneracy proportional to Q. Now, if we wanted to really analyze this completely, we also have to discuss the infrared dynamics of the gauge fields, so the U1, SU2, and SU3. And this can lead to new effects, and I will ignore them for now. I will say a little bit about the SU2, the U1 later. Now, let's now analyze the effects of Hawking radiation. So imagine now we have a near extremal black hole. So if you have a near extremal black hole, its energy will evolve. So it will lose energy, and we can apply what?
I have a question. You said the fermions will become massless, but all the generations will become massless, right?
Yeah, all of them. Yes.
What if in our world there actually were there were many more massive particles? They would all suddenly become visible if there were.
Yes. So if there was, yes.
I see. Okay, so I see.
Well, I mean, the thing is that I'm not sure you can add so easily generation. Well, I mean, you would have to have a very high Yukawa coupling for it not to be visible. I'm not sure it's compatible to have a.
I see. Okay.
I think there is probably a theoretical bound. I mean, maybe we haven't reached it yet experimentally, but.
Okay. Thank you. Yeah.
Yeah, well, I guess maybe I should also have said that this is assuming only the standard model. If there was some other new dynamics, if I don't know, there were extra dimensions, or there was, I don't know, any other new dynamics that you can have at higher energies, this could also be changed. Okay.
Okay, thank you.
Yeah. So, and well, you would have to do a similar analysis for that theory. But some of the features are fairly universal. So, so now we have the black hole at finite temperature, and we can apply the two-dimensional black body formula, saying that the energy emitted is proportional to the square of the temperature. So in 4 dimensions, it would be the 4th power of the temperature, and times the number of species of particles that we have, which is proportional to Q. And so this is somehow the energy that comes out of the black hole in this regime that the magnetic field is very large and everything is massless. And so this type of formula would be true for, let's say, very high temperatures, higher than, let's say, the electron mass, for example. And on the other hand, for a Schwarzschild black hole of the same temperature, we would have this other formula, which is temperature to the 4th times the area. The area is proportional to 1 over temperature squared. That's the formula that Spenta was talking about in the beginning. And we also get something proportional to t squared. So we could see, we see that here we have in the magnetic case, we have an extra factor of Q, and that greatly enhances the evaporation rate. So for example, if we had an uncharged black hole of a mass of a big mountain, let's say that's 10 to the 12 kilograms, this is a special mass because such a black hole that was created at the beginning of the universe would be evaporating roughly now. So it takes a time, the evaporation time of those black holes are the age of the universe. But if you had a magnetic black hole of the same mass, and you had, let's say, an order 1 deviation from extremality, by order 1 I mean a mass which is, let's say, twice the extremal mass, then the time it would take to decay to extremality would be of order milliseconds. Okay, so extremality is exponential with a time scale of order milliseconds. Now, this previous discussion was correct when the temperature is higher than the electron mass, so that we can approximate the electrons as being massless. But when the temperature becomes smaller than the electron mass, then we have an exponential suppression. We expect an exponential suppression of this kind, and that suppresses this more. That suppresses, well, the evaporation, so it wouldn't be as fast as just mentioned. Now, black holes violate global symmetries, so baryons could go in and leptons could come out, and so the black holes could catalyze proton decay. And so, for example, as a fun application, sort of science fiction application, we could have, imagine that we had a relatively light black hole, let's say a black hole of 100 kilograms, and then we could use this to get a significant amount of power. So, for example, in this case, the QCD radius is roughly the size of an atom, and probably once you get the baryon to that point, then it could basically go in. So it would be a matter of getting a sufficient number of baryons in this vicinity. And if it's not an outrageous number of baryons you need to get, I don't know, a megawatt of power. This is just a science fiction application. Of course, first you would have to find this 100 kilograms magnetically charged black holes. This phenomenon that the black holes can catalyze proton decay is very similar to a phenomenon of catalyzing proton decays by magnetic monopoles as opposed to black holes. And for this effect to be significant, it was also important that the fermions have these effectively massless two-dimensional modes that greatly enhance the effect. Because if you didn't have this feature, then okay, you might have perhaps some violation of baryon number in a region of order the size of the magnetic monopole, but that region is very, very tiny. And if you have any fermion at ordinary energies, they would have a wave function which is highly extended, and a very small portion of the wave function would be in this region. That's if you didn't have this effect we are discussing here. But somehow the fact that there is this effectively massless mode, two-dimensional mode, makes it very easy for the fermions to go into the center of the monopole. It somehow guides the fermions to the very tiny region near the core where the baryon number is violated. Here we have conceptually the same effect, except that everything is enhanced by factors of Q, because we have more magnetic charge, we have more of this effectively massless fermions, and so on. And also the baryon number violation is not due to the grand unified theory, but to black holes. Now, there is another thing that I didn't discuss in the paper, but I think it's probably also present, which is the fact that normally in the electroweak theory, you have sphalerons. And there was a recent paper claiming that when you have this vacuum with very high magnetic fields, these phaleron processes are not suppressed. And so that would be another way of violating baryon number. Okay.
And sorry, actually,
yes.
Juan, in that case, how does it happen that the Hawking evaporation violates the baryon number and the sphalerons also, and both are of the
yes.
same order, or how?
I haven't studied the sphaleron things. I think it might be the sphaleron processes might be more important actually, because they would occur in this region of the magnetic corona.
Mm-hmm.
So, but I have not studied that in detail. So.
Thank you.
I mean, I'm discussing here some effect which is easier to understand, but and this effect will violate both B and L and B minus L and so on. The sphalerons, of course, violate only B plus L. I mean, if you're interested in the power plant, it's enough to get the sphalerons, right?
Yes.
So.
Thank you.
Okay, so now let's discuss a bit the stability of these black holes. So we expect these black holes to decay by pair creation of magnetically charged objects, and the decay rate depends on the mass of these objects. And the more massive these magnetically charged objects are, the harder it is for the black hole to decay. So here was the sketch of the process. So in the near horizon region, you create a positively and negatively charged pair, and then in this way, the black hole would discharge. Now, the highest mass that you could have would be to have, for example, GAT-like monopoles or single charge black holes. And this maximum expected mass is of order the GAT monopole, or and also is the type of mass that you get from the weak gravity bound. So if you assume there should be a charge one object, then its mass should be of the order of the GAT monopole mass from the weak gravity discussion. So now if this was the case, then objects with charge bigger than about 1 million would be effectively stable over the age of the universe. And most of the black holes we discussed had charges bigger, so they're really stable over the age of the universe. So if they were formed in the beginning of the universe, they'll still be there. So it's different than other primordial, normally when you have very small primordial black holes that are uncharged, they evaporate quickly and they don't last till today. But if they were magnetically charged, then they could last till today. Now, one question you can ask is whether such black holes can be produced in the very early universe. So before we discuss the formation of magnetically charged black holes, let's just remember the mechanism for producing uncharged black holes. So uncharged black holes, so ordinary Schwarzschild black holes, or Kerr black holes, can be generated by a variety of mechanisms. So one interesting mechanism is to have large primordial fluctuations at some particular length scales. So imagine that this is the early universe during inflation, and then you have fluctuations at very different length scales. So at long distances, let's say you have some small fluctuations, but at some intermediate distance, you have very large fluctuations. So that's roughly what this picture is trying to signify. And then as time goes on, and you end inflation, and you reheat, and so on, when these length scales here enter the horizon, they will have very large fluctuations and will form black holes, which are roughly of the size of the horizon at the time. And with this mechanism, you can form black holes of any desired size. All you need to do is to make sure that your inflationary potential or inflationary evolution is such that it generates fluctuations at the appropriate length scale. Okay, and then it's a question of, well, whether those are natural or not natural, or fine-tuned or not, but that's a separate discussion. But at least it shows that there is a potential that can produce these black holes. And with this mechanism, you can produce them at various sizes. Now, other mechanisms would be like phase transitions or violence processes after the end of inflation, not related to the initial fluctuations. So those are the types of mechanisms that people have discussed. Now, if you try to produce the magnetic black holes, then one mechanism is what I would call the square root of n mechanism. And this type of mechanism has been discussed with slightly different applications in these other papers. And the idea is the following. So you first, after inflation, you produce a bunch of monopoles and anti-monopoles, and then we will use the mechanism that we had in the previous transparency. So we have large primordial fluctuations at some length scales. So this is here, we are discussing we have a picture of the large fluctuations, and the blue and red dots are the positive or negatively charged magnetic monopoles. And so the idea is that after you produce these black holes, each black hole will swallow about n magnetic monopoles, and the charges will be somehow randomly distributed. So we expect that the typical charge of each monopole would be square root of that n. Okay, so we form these black holes, and some will have some positive charge, and some will have some negative charge, and then they will evaporate. Then if they are small enough, they evaporate quickly enough. The effects we discussed make them evaporate more quickly, and then they will settle into very close to extremal magnetically charged black holes. So that's a mechanism. Again, I'm not claiming the mechanism is natural. I'm only claiming that it is possible. Okay, so.
Sorry, Juan, can I just ask a question? It's probably a dumb question, but yeah. Just in the early universe, normally people think of magnetic monopoles being produced in, say, gut theories through the Kibble mechanism, where you have this field. And could we just combine that with, then the monopole falling into its own gravitational radius or something?
Yes. I'm not claiming this is the only way to produce them.
Okay.
There might be more. Yeah, there might be more, let's say, coherent way to produce them that can produce bigger charges. So with this mechanism, you cannot produce very big charges. I forget now, but maybe up to maybe 1 million kilograms. About 1 million kilograms, perhaps. Not more. So yeah, because you need to make sure that the black holes evaporate quickly enough. And if you produce very large, if you want to have very large, the final charge Q is square root of n. So if you want to have very large charge, then you would need to have very, very large n. And if that n is very, very large, then they might not evaporate quickly enough. So yeah, those are some of the issues. But yeah, if there was a way to have some version of the Keeble mechanism that produced dominantly monopoles of a given charge and then make them collapse into a black hole, then that would be nice also.
Thank you.
Couldn't think of how to do that.
So
then there might, yeah.
Sorry, sorry, I just had a question. So is this a mechanism to kind of dilute the like number of magnetic monopoles? Usually the monopoles.
Yes. In fact, this paper argued for this mechanism for removing monopoles. Yeah.
And is it effective? Like, can we like not use inflation to dilute magnetic monopoles, but use this mechanism?
I'm not 100% sure, so I would refer you to this paper where I think that was the conclusion. Yeah, I guess usually inflation is cited as a way to do this, but of course inflation does other things too. So, but yeah, the way I see it is that this could be a mechanism for removing monopoles that you could have produced after inflation, for example. And this other paper, what they did is they used this mechanism for producing extremal black holes in the dark sector, but electrically charged. So this one had electrically charged black holes. It's a little easier to make electrically charged black holes. So, well, I think I'm more or less ending near the end of my time. I had here some transparencies about the dynamics of the U1 gauge fields. And there is a fun relationship to the so-called force-free electrodynamics. So I wanted to discuss that. So let's consider charge fermions in a magnetic field. For large magnetic fields, the main physics will be that of Landau levels. And we can consider the case of massless fermions in a magnetically charged field. So in a magnetic field, then we consider the theory of low energies compared to F. So we have the lowest Landau level. And in this setup, the fermions move along the directions of the magnetic field lines. Maybe I should go directly since I'm running out of time. So wait, what happened? Okay, so we have the magnetic field lines, and we have fermions that move along the magnetic field lines. So before we introduce any coupling to the U1 gauge field, we have one basically physical mode, which are fermions moving along the magnetic field lines. They have dispersion relation, which is p squared equal to 0, where p is the momentum along the magnetic field lines and also the energy, so along those two dimensions. But in particular, this dispersion relation does not depend on Q, which is the momentum here. That means that the fields along each of the magnetic field lines is an independent variable. On the other hand, we also have two modes, which are the two modes of the photon, which have the usual four-dimensional dispersion relation. So this is when there is no coupling. Once there is some coupling, there is a kind of Higgs mechanism which removes one of the components of the gauge field. Well, it's some combination of the gauge field and you could say the bosonized mode that describes these fermions. And then you're left with two modes. One which again has a dispersion relation similar to that of the fermions, so independent variables at each position. And then one which looks roughly like similar to the photon ones here. Now it turns out that these two modes, they can also be viewed as arising from a theory which is called force-free electrodynamics, and that describes the low energy dynamics of this system. So this force-free electrodynamics is can be derived by thinking about this problem and saying that you have originally the original gauge field action, and then you have the bosonized fermions, so the fermions will bosonize, and there is a boson that contains a gradient only along the directions of the magnetic field, but not the transverse dimensions. And then there is a coupling there. These bosons carry some charge, and you can, if you bosonize the chiral symmetry, then the charge coupling is through this, it has this form. And at low energies, that massive mode that we discussed, we can remove it by dropping this term, and we get the theory which is just electrodynamics with the constraint f wedge f equal to 0, or E dot B equal to 0. And this is so-called force-free electrodynamics. This derivation was done in paper by Thompson and Blaes, so with an astrophysics motivation. So this force-free electrodynamics has appeared in astrophysics in situations where the plasmas are dominated by magnetic fields. It's a kind of interesting theory. It's classically conformal invariant. It's non-trivial and interacting because we have this constraint. We can solve these constraints by writing A as in terms of two scalar fields. And we can think of, and we can then put this back in the action. We get some action with 4 derivatives for the scalar fields. Only 2 derivatives in time, but 4 derivatives in total. And it's a well-defined theory, at least classically. And we can think of these phi i's as the Lagrangian coordinates of a string fluid. So we can basically think of, after we consider this force-free electrodynamics, is roughly describing the magnetic flux lines now acquire a kind of dynamics, and they repel each other. So the 2 modes that we discussed are sort of transverse shear modes of this fluid of strings, or the compressional modes of the fluid of strings, which had this other dispersion relation. And in fact, we can change the compressional coefficient here by changing the Lagrangian from f squared to some function of f squared. So for example, we can put the Born-Infeld Lagrangian, and if we make the magnetic field very high, then we can set this coefficient to 0, and then we have something that looks more like free strings. Now, all of this is connected with plasma physics, magnetrohydrodynamics, Aflin waves, etc. And there is also some interesting way of deriving this force-free electrodynamics from thinking about one-form symmetries. So just classical electromagnetism is the theory where you have 2 one-form symmetries, an electric and a magnetic one, and the gauge field is just the Goldstone boson for those. But if you only have the magnetic one-form symmetry, then you derive this force-free electrodynamics. That's roughly what is done in these papers. Now, so these are this is some discussion of what the U1 dynamics does. Of course, in the full problem, there is also SU2 and SU3 dynamics that I have not discussed. Well, in conclusion, these magnetic black holes are interesting objects in the standard model. They naturally have very high magnetic fields. We can have a restoration of the electroweak symmetry in a relatively large region. We have this magnetic corona, and they have interesting effects for Hawking radiation, and they're interesting candidates for primordial black holes. Now, there are 2 extra points, 2 extra things you can say about them. So these are kind of more phenomenological, let's say, considerations. They're also interesting theoretically. We can use this type of black holes to construct traversable wormholes. And here, the key aspect is this fact that we have that the number of massless fields in the near horizon region is multiplied by Q. And so we have a large number of massless fields. And if we bring 2 such black holes together, a positively charged one and a negatively charged one, they can develop, it is possible to consider a configuration which has a wormhole going between them. And then there is here a closed loop, there can be negative Casimir energy, a quantum effect, which is enhanced by a power of Q. And the fact that we have that enhancement provides a control parameter, and you can actually form these wormholes in a controllable regime. I mean, you can find the solution in a controllable regime. Whether they form naturally and so on, it's more difficult. And it seems that they would not form very quickly. If you bring two black holes together, they would not, would take perhaps exponential time to form. At least we don't know of a mechanism where they would form in a polynomial timing queue. But anyway, it's interesting that these solutions can be shown to exist. Also, these four-dimensional black holes are well approximated by certain two-dimensional toy models of JT gravity plus a CFT that were recently discussed in many papers, probably starting with this paper here, and several others. And so when people discuss these models, sometimes they apologize by saying that they are talking about a toy model that is not realistic and so on. But this model is a good approximation to the physics of these four-dimensional black holes. Okay, there are many questions, so some are phenomenological. One is to see whether these production mechanisms, whether they can be made natural or whether how fine-tuned they are, and whether there are some constraints from astrophysics on how many such black holes could exist, and so on. And there are also some more theoretical questions, like find the proper infrared dynamics with very high magnetic fields, etc. Okay, thank you.
Thanks, Juan, for that very wonderful talk. We can now probably have more questions.
Are we allowed to clap once, please?
Yes. Yeah, we can unmute ourselves and clap.
My God. Thank you. I have one question, Juan. Can I ask it? So,
yeah, sure, please.
There is this whole issue of the problem of primordial magnetic fields in the universe. Is there any connection of if these type of black holes which you mentioned, after they Hawking radiate and settle down, they still will have some magnetic field, right?
Yes. Yeah, so they might play a role producing magnetic fields. They might also have a negative role in screening the magnetic fields that were produced, because if you had some magnetic fields, these black holes would move and produce them, and whether they either produce or screen the magnetic fields, I'm not sure. And people have discussed this type of questions in the context of magnetic monopoles. And there are some bounds on the density of magnetic monopoles that is based on the fact that they could screen the magnetic fields of the galaxy. And but also people have discussed in some other regime of parameters where they might play a role in generating the magnetic field. So I don't really know the answer. So I think so this question of constraints from astrophysics, I think it's interesting. And the problem seems to be somewhat similar to the problem of magnetic monopoles. So how many magnetic monopoles you could have and so on. The charge to mass ratio of these black holes is similar to the charge to mass ratio of the magnetic monopoles. But the difference is that they are more concentrated. I mean, you could have a bunch of black holes that, the difference between the two is that in the case of the black holes, they are more concentrated. And so maybe some of the constraints are different. So for example, for magnetic monopoles, there is an astrophysical constraint that comes from the fact that the magnetic monopoles can enter neutron stars and start producing neutron decay inside the neutron star and so on. So that might be changed with these black holes. It might be that it might be harder for the black hole to meet the neutron star, for example, and perhaps once it meets a neutron star, it makes it explode almost instantly. So the constraints might have a different nature.
Thank you.
Now, one fun point is the following. So people are discussing a certain planet 9, which is a hypothetical
Yes.
planet that of a few hundred Earth masses and so on. That it's, I don't know, maybe about a few hundred astronomical units from us and so on. And one group proposed that it might be a primordial charged black hole. So it would have a size of a few centimeters. So you could even wonder where that one could be a magnetically charged black hole. It's not 100% obvious whether it's ruled out or not. So, and it seems it might be ruled out for that particular case because the charged particles of the solar wind might end up in this black hole, and they would fall in, and they would then the Hawking radiation would be so big, or the radiation from these particles in the magnetic fields of this black hole would be so big that we would have seen it. But I'm not sure. I haven't done the calculation carefully. But I don't know. This is a type of question you can ask. I mean, wherever you had a primordial black hole, you could replace it by a magnetically charged black hole and ask. I think it's a kind of question we should be asking. Yeah.
So I had a sort of similar, perhaps crazy question. Suppose 1/100th of dark matter was your magnetically charged primordial black holes. Would we know that from observations? Would we have been able to tell? Would we have been able to tell that one if it was magnetically charged? Is that ruled out?
I don't know. Yeah, I would like to answer I would like to know the answer to this question. I don't have enough experience in these phenomenological constraints to be able to. I mean, it's different from. I cannot open the discussion for monopoles and immediately derive what the constraint is, because the objects are a bit different.
Sorry, Juan, I had a version of Shiraz's question, but just to re-ask it, why 100? Actually, let me ask my question in two parts because it's an opportunity to hear you. Could just dark matter be primordial black holes, according to you, or is that ruled out? I don't know the status, but then
yes.
If it's allowed, could it be a magnetically charged black hole, or then some fraction?
Well, okay. So I don't know the answer for this question. I don't know the answer. You could ask a similar question, which is, could dark matter be magnetically charged monopoles, GAT monopoles? Right? And so people analyzed this question in the 80s, and they conclude that it could not be. And there are two constraints. So one comes from the fact that the magnetic monopoles would screen the magnetic fields of the galaxy. And the other comes from the magnetic monopoles catalyzing neutron decay inside the neutron stars or other astronomical bodies. That one is a little more model dependent because you could consider various other magnetic monopoles which cannot catalyze proton decay. So, but yeah, so if you can catalyze proton decay, the strongest constraint comes from the neutron star discussion. But yeah, so but I don't. So for this case, it's different, right? Maybe if the collision with the neutron star is so spectacular, you might be cataloged as something completely different, and maybe it could have been missed. I don't know if it could have been missed. Maybe it would have been seen, and then there is a stronger constraint.
May I ask a question?
Thank you.
Yeah. You actually talked about extremal black holes which are charged and which have a mass. But I can imagine also these black holes having, extremal black holes having angular momentum. And will that somehow impact the analysis or the conclusions you have?
Yes. Well, yeah, so if they are rotating, they would, yeah. If you have a rotating black hole in ordinary electrodynamics, right? So the Kerr-Newman black hole.
Yes.
Okay, we can have rotation, and the rotation will exist forever. But as we discussed, the black hole is described by this force-free electrodynamics. And when it is rotating, it will emit energy, even classically. Already at the classical level, it will be emitting energy. Well, but perhaps I should say it more physically. So when the black hole is rotating, the purely magnetic field becomes also electric field. Yes, and yes. The electric, because we have these massless fermions, the massless fermions can start flowing out and can carry the angular momentum away. Okay, and this mechanism for carrying energy out of rotating black holes is roughly the same as the Blanford-Seignac mechanism for producing the jets in astrophysical black holes. In fact, their model consists of taking this magnetically charged black hole in force-free electrodynamics, and then patching, taking that black hole first as a model, and then they say, well, in a real astrophysical black hole, we have a disk, and then they patch a black hole with, let's say, positive magnetic field on the top part and negative magnetic field on the bottom part, and that's roughly the model for the extraction of energy from of the powering of the jets and so on, extraction of energy of rotating black holes for quasars. But anyway, so if you just put in the numbers for a rotating black hole when the black holes are small and the kind that we were kind of discussing, then they spin down quickly. So you can take this small characteristic timescale.
Okay. Thank you.
Sorry, just to understand. So Juan, you're saying even if you took an extreme Kerr-Newman, which was magnetically charged, and then of a small enough size so that the magnetic fields are, like you're saying, then they will emit these massless fermions and spin down. Is it to again settling perhaps to the non-rotating magnetically charged black holes?
Yes. The magnetic charge cannot change, so it will settle down to the.
I see.
It's not emitting some net electric charge. It's just producing some currents that modify the magnetic field, and in the end, they produce a flux of radiation to infinity.
I see.
And this happens so fast.
Sorry, just one small thing, Shiraz, please. So from that point of view, the non-rotating extremal magnetically charged black holes are a more natural cosmological object to think about, right?
Yeah, that's right.
Thank you. Go ahead.
Sorry. And the spin down happens so fast because the same parameter that makes the black hole big also is involved in the number of fields that can be emitted.
Yes. So one way to understand it is that so you have it would be described by classical theory, which is GR plus force-free electrodynamics. Okay, and that theory has the parameter of the electric charge as usual and so on, but that can be essentially removed from the equations, and then you have radiation at the classical solution. This was discussed in a nice paper by Jacobson and Graglia. Samuel Graglia. Jacobson, they had a very nice review on force-free electrodynamics, and they discussed how a magnetic monopole that is rotating, magnetic monopole source that is rotating even in flat space would emit this classical radiation. So in force-free electrodynamics, a uniformly rotating object like this produces outgoing radiation. This is different than ordinary electrodynamics, where if you have a uniform rotation, you wouldn't produce radiation.
Sorry, may I ask a question?
Yes.
Maybe it's a little bit naive, but did you think about talking about constraints? Presumably from the observations already from all the binary black holes that have been observed, can you put bounds on how many magnetically charged black holes there may be. I mean, the rates of the binaries that they have observed is very large, so they are not magnetically charged. So did you think about this?
Well, the short answer is no, but let me just, in principle, there should be a bound on their electric or magnetic charge, right? Now, one point that is important to consider is that the emission of radiation, of electromagnetic radiation out of binary is larger than the rate of gravity wave emission. And so presumably you would observe the effect in the black holes would emit energy in a different way. So you would have to compare to a different template.
Yeah.
I have asked Matthias Aldaria, who has done this. He told me people did not put an explicit bound. He told me one could put the bound, but I haven't done the analysis. Apparently, he said that it would be not too difficult to extract the bound from the bounds that have already been put. Possible deviations of the the emission of gravity waves as the two black holes are getting closer together, and how the frequency shifts. So if you are emitting energy faster, then the frequency will shift faster. Right?
Yeah. Okay. Yeah.
Yeah.
Thanks.
Hi.
Another more important point, perhaps I should mention, is that, I mean, the amount of energy that would be emitted in electromagnetic waves. Well, let's first make a more serious order point. Let's just ask whether the two black holes could be extremal, right? Magnetic. So I think this is not possible because the amount of energy that would be emitted in electromagnetic radiation would be comparable to at the final stages would be comparable to the amount of energy in gravity waves, right? And that amount of energy is very big, right? It's a few solar masses. So I think we would have been seeing an optical. But in principle, yeah, you could have some bound that maybe, just the fact that you don't see the electromagnetic radiation probably is what sets the strongest bound, perhaps.
Yeah. Okay. Yeah. Thanks.
I mean, you could imagine. So the previous discussion I made, I mentioned about trying to get the spin down and so on. This would apply in case that the black holes were charged either electrical or magnetically under a dark Q1. I mean, it could be that it's a dark Q1, so maybe you don't see the electromagnetic because. Yeah, so presumably this is some part. It's another parameter that should be fit into the LIGO discussion.
Yeah, thanks.
Hi, I just have a general question.
Yes.
There's a conjecture that relates black hole partition function to topological strings. So I just wanted to ask, firstly, like in general, what is your opinion about that conjecture? And secondly, does black hole partition function plays any part in your current work that you presented?
Well, those discussions are particularly useful in supersymmetric theories, so black holes in supersymmetric theories, where we can actually calculate those partition functions. Yeah, so those are very useful for understanding sort of quantum aspects of black holes and yeah, the relationship between the microstates and the entropy and so on in great detail. So they've been very useful for that. They don't play a role in what we are discussing here. Yeah. I mean, we don't have as much control on the theory as we have in those supersymmetric examples.
I mean, black hole partition function is a classical property.
Well, but if you want to, well, I mean, to lead in order, of course, you can calculate the partition function would be given by the black hole entropy, and then you would have to start computing the quantum corrections. Now, those quantum corrections, in principle, you can start computing them. As we said, for these black holes, well, you could compute the corrections. There would be, you would have to do loops of matter and of these matter fields, and maybe also the U1, SU2, SU3 gauge fields, etc. And yeah, so you could do that computation. So the computations of the extremal entropy and corrections to the extremal entropy. Yeah. So at least perturbatively, you could certainly do that computation. Non-perturbatively, there will be issues with the fact that the black hole can decay. So the whole thing is not well defined non-perturbatively, or you have to be careful about how you define it non-perturbatively. But even doing the computation in perturbation theory sounds a little difficult. But I mean, maybe it could be done at least to the first few orders, just to see what one gets.
Do we have any other questions?
Maybe make another comment, which is that this type of magnetic black holes, they were, or similar situations were discussed a lot in the ADS context. So magnetically charged black holes in ADS and in the context of considering matter in magnetic fields and so on. So in the context of ADS DMT.
May I ask one question?
Yeah.
Yeah. So this is probably more related to your four-dimensional wormhole paper.
Yes. Yes.
So there, I can see that the same quantity Q, which makes the black hole big, that also makes the number of Landau levels of fermions. But eventually, you use that to violate the Anik condition by saying that Casimir energy, which is supposed to be like a 1 over n effect compared to the classical energy. So there is a competition between a quantum effect and a classical effect because of the largeness of Q. So I'm just wondering how how still the semi-classical analysis.
Right. I think the philosophy is similar to the Banks-Sachs fixed points. So when maybe this might be more familiar to you. So there is this discussion of finding fixed points in SUN theories with n flavors.
Yes.
So in that case, the crucial point is that, and you balance a one loop versus the two loop beta function. But something that is important is that first you sit near a point in parameter space where the one loop beta function is almost 0. And then the two loop beta function is, well, has a 1 over n and so on, but is for the 1, or has a proportional to a small coupling. It has an order 1 coefficient, but the one loop term is anomalously small because of the ends of the cancellation between the number of flavors. Now, in this case, you have something similar in the sense that the wormhole is classically almost a solution. So it's not a solution. The wormhole is not classically a solution,
right,
but it is almost a solution when the wormhole is very, very long. So and the parameter there is how close you are to extremality. So the closer you are to extremality, the longer the wormhole, and the closer it is to a solution. But it's not a solution. And then the quantum effect, well, it's there and it's enhanced by this power of Q and can compete with this small classical force, if you wish. That, that is the basic idea.
I see. Okay. Thank you.
Yeah, sure.
Do you have any more questions? Okay, if you don't have any more questions, let's thank Juan once more for giving us this beautiful talk, and we hope to see you next week. We have the next seminar next Wednesday at 3 p.m. Indian Standard Time. Okay.
Thank you, Juan.
Okay. Thank you. Bye, everybody.
Bye, Juan.
Thank you.